The control stick wouldn't respond the way it was supposed to. That was the point. Flight Lieutenant James McLaughlin had spent 3 nights in a freezing hangar with a hacksaw, wire cutters, and a growing sense that what he was about to do would either save his life or end it. The modification he made violated every principle in the Royal Air Force Technical Manual. It contradicted the accumulated wisdom of aircraft designers who had spent years calculating optimal control ratios. And on the morning of March 7th, 1941, over the grey waters of the English Channel, it would allow him to do something that should have been aerodynamically impossible. Outturn 3 Messerschmitt 109s, simultaneously in a dogfight, where the math said he should have died in the first 30 seconds. This is the story of an unauthorized modification made by a pilot who understood something the engineers didn't. But it's really about the moment when desperation meets insight, when the gap between what you're taught and what you need becomes a matter of survival. And what it reveals about the difference between following procedures and understanding principles, between obedience and innovation, between the way things are supposed to work and the way they actually work when your life depends on getting it right. March 1941, RAF Tangmere, southern England. James McLaughlin was 24 years old, missing his left arm below the elbow, and according to every regulation in existence, he shouldn't have been flying at all. The prosthetic he wore was crude even by 1941 standards, a leather socket with a metal split hook that could grip but not feel. He had lost the arm 9 months earlier over Dunkirk when cannon shells from a 109 had torn through his cockpit and his forearms simultaneously. The doctors had been sympathetic but clear. His flying career was over. The Air Ministry had been less sympathetic and equally clear. One-armed pilots were not operationally viable. McLaughlin had spent 6 months proving them wrong through a combination of stubbornness, adaptation, and a willingness to accept that he would have to fly differently than everyone else. He had returned to operational status in January 1941, assigned to No. 261 Squadron, flying Hurricanes on convoy protection duty. But here's what the medical boards and the bureaucrats hadn't understood. Losing an arm hadn't just changed how McLaughlin flew, it had changed how he thought about flying. When you lose a limb, you don't just lose function. You lose the unconscious grace that comes from having 4 working extremities. Every action requires thought, planning, compensation. McLaughlin couldn't simply grab the throttle with his left hand while his right hand managed the stick. He had to choose, throttle or stick. He couldn't casually flip switches with his left while maintaining control with his right. Every input required deliberate sequencing. And in the brutal calculus of 1941 air combat, where dogfights were decided in seconds and hesitation measured in bullet holes, this should have been fatal. Except McLaughlin had discovered something. The limitation forced him to think about control inputs differently. When you can only do one thing at a time, you become very good at choosing which thing matters most. And he had begun to notice something about the Spitfire's controls, something that troubled him, something that the able-bodied pilots around him seemed not to see because they had the luxury of compensating for it without thinking. The Spitfire's ailerons were heavy, not intolerably heavy, not prohibitively heavy, just heavy enough that rolling the aircraft at high speed required significant force on the control stick. For a pilot with 2 strong arms, this was manageable. You pushed, the stick moved, the aircraft rolled. Simple. But McLaughlin, with his prosthetic left arm, couldn't help the way able-bodied pilots helped. He couldn't use his left hand to push against his right knee for leverage. He couldn't grip the side of the cockpit to brace himself while forcing the stick over. He had to do it all with his right arm, and at speeds above 300 miles per hour, the aerodynamic forces on those ailerons made quick rolls exhausting and slow, which meant that in a dogfight, when a Messerschmitt snapped into a hard turn, McLaughlin's Spitfire responded like it was thinking about it. The engineers had designed it this way deliberately. Heavy ailerons meant stable flight. They meant you couldn't accidentally over-control the aircraft. They meant smooth, predictable handling that wouldn't surprise novice pilots. The design philosophy was sound. Make it safe, make it forgiving, make it difficult to lose control. But McLaughlin had spent enough time being shot at to know that safe wasn't always safe. Forgiving could get you killed. And the greatest danger wasn't over controlling your aircraft. It was under controlling it while someone tried to murder you. So he began to experiment, not officially, not through proper channels. Those channels would have required submitting proposals, waiting for engineering reviews, explaining to people who had never been shot at why their carefully calculated design was insufficient. McLachlan didn't have time for that process, and he suspected it wouldn't matter anyway. The people who made the decisions were the people who had designed the controls to be heavy in the first place. Instead, he started reading, not pilot manuals, engineering texts, borrowed from a friend who had studied aeronautical design before the war. And what he learned was both simple and profound. The stiffness of an aircraft's controls is not a fixed property. It's a mechanical relationship between pilot input and control surface movement. Change the relationship, change the stiffness. The technical term was control gearing ratio. For every inch you moved the stick in the cockpit, the ailerons moved a certain number of degrees. Decrease that ratio. Make the ailerons move more for the same stick movement, and suddenly the controls feel lighter. Not because you've made the ailerons physically easier to move, but because you've reduced how far they need to move to achieve the same roll rate. The concept was elegant. The implementation was going to be dangerous, possibly illegal, and definitely unauthorized. What McLachlan was proposing was a fundamental alteration to the control linkage of a military aircraft, the system that connected pilot input to flight control surface. In a Spitfire, this system was a complex arrangement of rods, bell cranks, and cables running from the control stick through the fuselage to the ailerons in the wings. The gearing ratio was built into the geometry of these bell cranks, the L-shaped levers that translated linear motion into angular motion. Change the attachment point on a bell crank, change the leverage, change the ratio. Simple in theory. In practice, it meant taking apart the control system of a frontline fighter aircraft without authorization, modifying components that had been engineered and tested by people who actually understood structural loads and fatigue, and then putting it back together in a configuration that existed nowhere in any technical documentation. If it worked, he would have a Spitfire that responded faster than any other Spitfire in the RAF. If it failed, if his calculations were wrong or his modifications introduced flutter or structural failure, he would die. Possibly spectacularly. Definitely alone, because he wasn't going to tell anyone what he was doing until after he knew it worked. Late February 1941. The hangar at Tangmere after dark. McLachlan had volunteered for night guard duty, which gave him unsupervised access to his aircraft and an excuse for being in the hangar when he shouldn't be. The Spitfire Mark II he flew, serial number P8068, sat in the dim light like a sleeping predator, graceful and deadly, and about to be modified by someone who was definitely not a trained aircraft mechanic. He had spent weeks studying the control system, tracing every rod and cable, understanding how force traveled from his hand to the aileron hinge. The modification he planned was both simpler and more complex than he had initially thought. Simpler because the basic principle was just leverage, moving the attachment point on the aileron bell crank to change the mechanical advantage. More complex because that bell crank was attached to a system that had been carefully balanced, and changing one ratio meant changing others, meant calculating new loads, meant hoping that the structure could handle forces it hadn't been designed to experience. He worked carefully, removed the access panels, disconnected the cables, removed the bell crank, and then, with a hacksaw and a file and a precision that surprised him, he cut a new attachment hole 3/4 of an inch inboard from the original. 3/4 of an inch. The difference between a control system certified by experienced engineers and a control system modified by a one-armed pilot who was very good at mathematics, but had never actually designed anything meant to keep someone alive at 400 miles per hour. He reattached the bell crank with the cable now connected at the new position, closer to the pivot point. More movement at the aileron for less movement at the stick. He calculated that the ratio had changed by approximately 30%. That meant 30% more aileron deflection for the same stick input, which meant 30% faster roll rate. Or it meant 30% more load on the control cables, or it meant control flutter that would tear the ailerons off in flight. He wouldn't know until he flew it. He reassembled everything, replaced the panels, cleaned up the metal filings, and then he sat in the cockpit for a long time, looking at the control stick, thinking about what he had just done. In the morning, he would take off. He would fly the aircraft gently at first, test the controls at low speed, feel for any indication that he had just turned a fighter into a death trap. And if it felt wrong, if there was any vibration or unusual resistance or hint of structural complaint, he would land immediately, confess what he had done, accept whatever consequences followed. But if it felt right, if the controls responded the way he needed them to respond, then he would have something no other pilot had. A Spitfire modified not for what the designers thought pilots needed, but for what one pilot knew he needed to survive. The first test flight was terrifying, not because anything went wrong, because nothing did. McLaughlin lifted off just after dawn, climbed to 8,000 feet and gently, carefully moved the stick. The Spitfire snapped into a roll so fast he gasped, not violently, not uncontrollably, just instantly responsive, like the aircraft had been waiting for permission to move and finally received it. He rolled level, breathed, tried again. Same result. The stick pressures were light, almost delicate. Where before he had to shove the stick to get rapid roll response, now he could flick it. At high speed, where the original controls had felt like moving furniture, the modified system felt like conducting music. He spent an hour testing, rolling left and right, varying speed, checking for flutter, feeling for any indication that the structure was unhappy. Nothing. The aircraft was stable, responsive, transformed. When he landed, he said nothing to anyone. He filed the routine post-flight report. Aircraft serviceability normal. And he waited for the next scramble, the next time he would meet Messerschmitts, the next opportunity to discover whether his modification was innovation or suicide. March 7th, 1941. The scramble came at mid-morning. Convoy Protection Patrol, a formation of merchant ships crawling along the coast under grey skies. McLaughlin took off with 3 other Spitfires from 261 Squadron. The mission was simple, boring, vital. Orbit the convoy, watch for German bombers, hope the 109 stayed on their side of the channel. They didn't. 20 minutes into the patrol, ground control radioed vectors to hostile aircraft, bearing east, altitude 12,000 feet. McLaughlin's section turned toward the contact, and there, stepping down through broken cloud, 3 Messerschmitt 109Es in a loose Vic formation, hunting. The geometry was bad. The 109s were higher, faster, and had seen the Spitfires first. The German formation split. One 109 continued toward the convoy. The other 2 rolled inverted and dove, converting altitude into speed, positioning for a slashing attack. This was the Luftwaffe's preferred tactic in 1941. Dive from above, make one high-speed firing pass, and climb away before the Spitfires could turn. It worked because the 109 was faster in a dive and could outclimb the Spitfire at low altitude. The defense was to see them coming and turn hard, denying them a shot. McLaughlin's wingman called the attack and broke left. McLaughlin broke right, not away from the threat, into it. The 2 109s were committed to their dive, wings level, speed building past 350 miles per hour. They expected the Spitfires to turn defensively, to break away. McLaughlin turned toward them, a hard climbing turn that pointed his nose not at where the 109s were, but where they were going to be. Standard deflection shooting. Except at the speed he was pulling, with the angle he was generating, the standard Spitfire wouldn't have responded fast enough. The heavy ailerons would have delayed his roll, slowed his turn, given the 109's time to adjust. McLaughlin's modified Spitfire snapped through the roll like it was cheating physics. The lead 109 flashed through his gun sight. He fired 240 rounds of .303 caliber and 20mm cannon in a 3-second burst. Tracers arced across the space between them. The 109 staggered, rolled inverted, and dove away, trailing smoke. No time to watch. The second 109 was already adjusting, pulling up from his dive, rolling to bring his guns to bear. McLaughlin was still inverted from his attack on the first aircraft. Instead of rolling upright first, which would cost time and energy, he pulled straight down while inverted, yanking the nose through the horizon in a split S that converted his altitude into speed and pointed him back toward the fight. The G-forces pressed him into his seat. 6, maybe 7 gravities. Enough to grey his vision at the edges, but the controls responded, light, immediate. When he needed to roll upright, the stick moved like it was thinking with him. The second 109 tried to follow but couldn't match the turn rate. McLachlan came out of the split S with the 109 in front of him, full deflection shot fired again. Missed. The 109 pilot was good, jinking hard, using his aircraft's superior roll rate. Except McLachlan's roll rate wasn't inferior anymore. The 109 snapped left. McLachlan snapped left faster, staying inside the turn. The 109 reversed right. McLachlan reversed faster. They were turning at the same radius now, but McLachlan was responding to each direction, change a fraction of a second quicker, and in a dogfight, fractions accumulate. After the 4th reversal, McLachlan was gaining angle. After the 6th, he had a shot. He fired. The 109's canopy disintegrated. The aircraft snap rolled, flicked into a spin, and disappeared into the clouds below. McLachlan pulled hard, climbing, looking for the 3rd aircraft, found him 3,000 feet above, positioned for another diving attack. Alone now, probably watching his 2 wingmen go down. Calculating odds. The 3rd 109 turned away, dove for the deck and ran for France. McLachlan didn't chase. He had fuel to monitor and a convoy to protect. But as he turned back toward the formation of merchant ships, as his heart rate began to slow and his breathing steadied, he understood what had just happened. He had been outnumbered 3-1. The 109s had tactical advantage, altitude and speed. In every training scenario, in every tactical doctrine, he should have been defensive, should have survived by evading, should have been grateful to escape without damage. Instead, he had attacked into superior numbers and outmaneuvered 2 experienced Luftwaffe pilots in aircraft that were specifically designed to outturn the Spitfire at certain speeds. He had done it because his aircraft responded differently than theirs, responded differently than they expected, responded differently than any other Spitfire in the RAF. When he landed, his squadron commander was waiting, demanding to know what had happened. McLachlan described the engagement. 2 109s damaged or destroyed, 1 driven off. The commander studied him for a long moment, then asked how. McLachlan hesitated. Telling the truth meant admitting unauthorized modification, meant possible grounding, meant the end of the experiment, but the lie felt worse. So he told the truth. He explained the modification, the changed control ratio, the lighter stick forces. He waited for anger, for accusations of recklessness. The squadron commander listened without interruption. Then he did something McLachlan hadn't expected. He asked if the modification could be done to other aircraft. McLachlan said yes, carefully, emphasizing that he couldn't guarantee it was safe. Couldn't promise that every aircraft would respond the same way, couldn't take responsibility for anyone else's choice to try it. The commander nodded slowly. Then he pointed at his own Spitfire and said, "Do mine next." Within a week, 6 aircraft in 261 Squadron had modified controls. Within 2 weeks, pilots were reporting similar results. Faster roll response, lighter stick forces, improved turning performance at high speed. Within a month, Air Ministry engineers arrived at Tangmere to investigate unauthorized modifications to His Majesty's aircraft. They brought clipboards and regulations and deeply held concerns about structural integrity. They also brought test pilots and instrumentation. They flew the modified Spitfires, measured the control forces, analyzed the structural loads, and then they did something that bureaucracies rarely do. They admitted the unauthorized modification was an improvement. But here's where the story becomes complicated, where the clean narrative of innovation, triumphing over regulation, collides with the messy reality of engineering and human systems. The Air Ministry engineers didn't simply approve McLachlan's modification and order it implemented across the fleet. They studied it, refined it, tested it more extensively. They discovered that McLachlan's 3/4-inch change worked beautifully on the Mark II Spitfire, but created problems on the Mark V with its different wing and aileron design. They found that the modification improved roll rate, but increased pilot workload at very high speeds, where the light controls could lead to over-controlling. They determined that the optimal control ratio was actually different from what McLachlan had chosen. lighter than stock, but not as light as his combat-modified version. And then they spent 2 years developing and implementing a revised control system that incorporated the principle of McLaughlin's discovery while addressing the complications he hadn't encountered because he had only modified one aircraft and flown it in specific conditions. This is how progress actually works, not the clean story of lone genius defeating institutional incompetence. The more complex truth of individual insight, revealing possibility and institutions doing the unglamorous work of turning possibility into reliable implementation. But let's return to McLaughlin, because the modification wasn't just about aerodynamics. It was about what happens when limitation forces innovation. Think about his position, missing an arm, told he couldn't fly, allowed to return to combat, only because the RAF was desperate for experienced pilots. Every flight a test of whether his adaptation was sufficient, and instead of just trying to fly normally with a disability, instead of attempting to compensate for what he'd lost, he had studied the system until he understood it well enough to change it. This is different from courage. Courage is facing fear. This is something else. The willingness to question whether the way things are done is the way things must be done, the ability to see problems that others don't see because they're not forced to see them. McLaughlin saw that the Spitfire's controls were too heavy because he couldn't help with his left arm the way other pilots helped without thinking. That limitation made him aware of the problem. But awareness alone doesn't lead to solution. The crucial step was believing that the problem was solvable, that the engineers who designed the system might have optimized for different priorities than the ones that mattered in combat. This is a dangerous belief. Question the experts too readily and you end up with conspiracy theories and contempt for expertise. Question them too rarely, and you end up with systems that serve the designer's assumptions rather than the user's needs. McLaughlin navigated this tension by doing his homework. He didn't just decide the controls should be lighter. He studied why they were heavy, understood the engineering reasoning, calculated what would happen if he changed the ratio. His modification worked not because he ignored expertise, but because he extended it, applied engineering principles to a specific problem the original designers hadn't fully considered. The original designers had optimized for controllability and safety for average pilots in average conditions. McLaughlin optimized for maximum performance for experienced pilots in combat. Both priorities were valid, but in 1941, over the English Channel, with Messerschmitts diving from above, McLaughlin's priority was survival, and his modification gave him a fraction of a second advantage in roll response. In a dogfight, a fraction of a second is the difference between shooting and being shot. Now think about the 109 pilots he fought. They were flying aircraft designed by some of the best aeronautical engineers in the world. The Messerschmitt 109 was a remarkable machine, arguably superior to the Spitfire in several performance categories. Its pilots were experienced, well-trained, confident, and they entered that fight with every expectation that the mathematics of the engagement favored them. 3 against 1. Altitude advantage, speed advantage. They would dive, attack, and climb away before the lone Spitfire could respond effectively. Except McLaughlin responded impossibly. When they expected delay, they got instant reaction. When they expected to outturn him, they found themselves outturned. The tactical advantage they thought they had evaporated because one critical assumption was wrong. They assumed they knew how fast a Spitfire could roll. They assumed it because every Spitfire rolled the same way, except McLaughlin's didn't. This is what happens when asymmetric information enters combat. The 109 pilots were making decisions based on accurate knowledge of standard Spitfire performance. That knowledge became a liability when the aircraft they faced wasn't standard. McLaughlin knew his aircraft could do things theirs couldn't. They didn't know that. So when he rolled into them instead of away, when he matched their reversal rate, when he stayed inside their turns, their tactical decision-making was based on false assumptions. By the time they realized their assumptions were wrong, one of them was smoking and diving for safety, and the second was watching his canopy disintegrate under cannon fire. The third pilot, watching from above, learned instantly what the first two learned fatally. This Spitfire was different. He made the correct decision based on updated information. Leave. The engagement lasted perhaps 90 seconds. 3 experienced pilots, 3 capable aircraft, tactical advantage, defeated by one pilot whose aircraft responded differently than expected. But let's be clear about what this doesn't mean. It doesn't mean McLaughlin was a better pilot than the Germans. It doesn't mean the Spitfire was superior to the 109. It means that in one specific engagement, under specific conditions, an asymmetric advantage created a decisive edge. The 109 pilots weren't incompetent. They were surprised. Surprise is lethal in air combat. McLaughlin created surprise not through deception, but through modification. He changed one variable in a complex system, and that variable happened to be the one that mattered most in that particular fight. If the engagement had happened at low altitude, where the 109's better climb rate mattered more, the outcome might have been different. If it had been a diving attack without the turning fight, the modification might have been irrelevant. Tactics, conditions, and luck all mattered. But the modification gave McLaughlin options he wouldn't have had otherwise. It turned a defensive situation into an offensive opportunity. And in March 1941, when Britain was still fighting alone, when every convoy mattered, when every pilot lost was irreplaceable, that opportunity was the difference between merchant ships reaching port and submarines having easier targets. The Air Ministry's investigation into McLaughlin's modification revealed something uncomfortable about organizational design. The engineers who had developed the Spitfire's control system were brilliant, experienced, and had made reasonable decisions based on reasonable priorities. But those priorities included pilot safety, ease of training, and forgiveness for novice pilots. All admirable goals. All appropriate for an aircraft that would be flown by pilots with varying skill levels. But combat pilots weren't average. They were the survivors, the ones who had learned through experience what mattered and what didn't. And what combat pilots needed wasn't always what training command thought they needed. This tension exists in every organization that tries to serve multiple constituencies. Design for the average user and you disappoint the expert. Design for the expert and you endanger the novice. The Air Ministry had chosen to design for safety and accessibility. McLaughlin had modified his aircraft for performance and responsiveness. Both choices were defensible, but only one kept him alive on March 7th. The eventual compromise was telling. The RAF introduced modified controls as an option, not a mandate. Experienced pilots on operational squadrons could request the lighter control system. Training units kept the heavier stock controls. This acknowledged that different contexts required different trade-offs, that there was no single optimal solution, only solutions appropriate to specific situations. McLaughlin continued flying combat operations until October 1943, when he was shot down over Tunisia, survived the crash with severe injuries, and finally accepted that his body had absorbed as much damage as it could. He had flown for 3 years with one arm, scored 5 confirmed victories, and influenced the design of every Spitfire built after 1942. But the victory count misses the point. The real achievement was seeing a problem others didn't see because they didn't have to, believing it was solvable, doing the work to solve it, accepting the risk of being wrong, and then proving through survival that the modification worked. This sequence, problem identification through limitation, study, implementation, risk acceptance, and validation through use, is how actual innovation happens. Not in laboratories with unlimited time and resources, not through carefully managed programs with review committees and staged approvals. In hangars after dark, with hacksaws and hope, by people who need something to work because their life depends on it working. Now let's talk about what this reveals about the relationship between user and designer, between the person who creates a system and the person who depends on that system under extreme conditions. The engineers who designed the Spitfire never experienced combat. They understood aerodynamics, structures, and control systems. They could calculate flutter speeds and load factors. But they couldn't know what it felt like to have a Messerschmitt on your tail. Closing at 60 miles per hour overtake speed, cannon already firing. Every survival instinct screaming for your aircraft to respond faster than it was designed to respond. McLaughlin knew that feeling intimately. He knew it with one arm. He knew it with degraded physical capability. He knew it with a certain knowledge that hesitation equaled death. That knowledge gave him perspective the designers couldn't have, and that perspective revealed that one of the design decisions, control system stiffness, was optimized for the wrong constraint. The designers had optimized for what would happen if a pilot made a mistake. McLaughlin optimized for what would happen if he didn't make mistakes, but still needed more performance. This difference in optimization targets is fundamental. Design for failure prevention, and you build in safeguards, margins, forgiveness. Design for success maximization, and you build in responsiveness, capability, edge. Modern systems thinking tries to balance both. But in 1941, that balance didn't exist yet. The Spitfire was designed for failure prevention. McLaughlin modified it for success maximization. The cost was reduced safety margin. The benefit was increased capability. He accepted that trade-off because from his perspective, the original safety margin wasn't safe at all. It was getting people killed. This is the paradox at the heart of his story. The engineers thought they were making the aircraft safer by making the controls heavier, less sensitive to inadvertent input. And for inexperienced pilots learning to fly, they were right. Heavy controls prevented over-controlling, prevented loss of control from excessive input. But for experienced pilots in combat, heavy controls prevented the rapid maneuvers necessary for survival. So the safety feature became a hazard, and the hazard mitigation became the risk. McLaughlin understood this inversion because he lived in the inverted context. The engineers, designing from the normal context of training and general operation, couldn't see it. When the Air Ministry engineers finally tested his modification and admitted it worked, they were really admitting something larger. That expertise about a system doesn't automatically translate to expertise about every use case for that system. The engineers were experts in aircraft design. McLaughlin was an expert in not dying. Both forms of expertise were necessary. Neither was sufficient alone. The breakthrough came from combining them, from the combat pilot, learning enough engineering to modify the system and the engineers respecting the combat pilot's needs, enough to investigate rather than dismiss. This collaborative validation is rare. Usually the user complains and the designer defends. The user says the system doesn't work. The designer says the user is wrong. Both dig in. Nothing improves. McLaughlin avoided this trap by not just complaining but modifying. Not just wishing for better controls, but calculating what better would require. And the engineers avoided it by not just defending their design, but testing the modification with genuine curiosity about whether a one-armed pilot might have seen something they missed. That mutual respect for different forms of expertise is the reason the modification became official, the reason later Spitfires had improved controls, the reason McLaughlin's insight benefited pilots who never knew his name. But let's talk about risk, because what McLaughlin did was objectively dangerous. He modified a flight control system without authorization, without supervision, without backup. If the modification had failed, if he had introduced flutter or structural weakness, if the first hard maneuver had torn a control surface off, he would have died. No ejection seat, no parachute time at low altitude. Just augering in and explosion and a brief report. Aircraft lost due to structural failure, cause unknown. That's not bravery. Bravery is facing a known danger for a worthy cause. McLaughlin was facing an unknown danger, one he created, for a cause he believed in but couldn't prove in advance. That's different. That's the willingness to bet your life on your own judgment, your own calculations, your own understanding of a complex system that experts spent years designing. Think about the arrogance that requires, and also the humility. Arrogance to believe you can improve on the work of experienced engineers, humility to spend weeks studying their work first, to understand their reasoning before contradicting it, to test carefully and be prepared to admit if you were wrong. McLaughlin had both. The arrogance showed in his willingness to modify the aircraft. The humility showed in how carefully he did it, how thoroughly he tested, how ready he was to abort if anything felt wrong. This balance is vanishingly rare. Most people with the arrogance to attempt what he attempted lack the humility to do it carefully. Most people with the humility to study carefully lack the arrogance to actually implement. McLaughlin had both, probably because losing his arm had already taught him that the authorities' judgment about his limitations could be wrong. If they were wrong about whether he could fly, Maybe they were wrong about how the controls should work. That seed of doubt about institutional judgment, planted by his successful fight to return to flying, gave him permission to question the control system design. Without that precedent, he might have assumed the engineers knew best. But he had already proven that experts can be wrong about capability. So maybe they were wrong about controls too. After the war, McLaughlin's modification became a footnote in Spitfire development history, mentioned briefly in technical analyses, usually attributed to Air Ministry engineers, rather than to the pilot who actually invented it. This is how institutional memory works. Individual contributions get absorbed into the collective, credit diffuses, the story gets simplified. The official history says the Spitfire's controls were improved over time through ongoing development. True, but that development was directly influenced by one pilot who refused to accept that the way things were was the way things had to be. This isn't injustice, it's just how complex systems evolve. Ideas come from individuals. Implementation requires institutions. Credit belongs to both. But if you read the technical reports carefully, if you trace the references back through engineering memos and test pilot evaluations, you eventually find a note. Modified control system first tested operationally on Spitfire P-8068, 261 Squadron, March 1941. That was McLaughlin's aircraft. That was his modification. The note doesn't say why it was modified or by whom, but the date is there. The evidence remains. The truth persists even when the story is forgotten. So what does this reveal about human nature, about war, about the gap between design and use, between theory and practice, between the way we plan and the way we survive? It reveals that systems designed for safety can become dangerous when the context changes. It reveals that expertise is narrow and specialized, valuable within its domain but blind to conditions outside that domain. It reveals that desperation plus insight can generate innovation that comfort never discovers because comfort has no incentive to question what works well enough. McLaughlin's modification emerged from necessity. He needed controls he could operate effectively with one arm. That limitation forced awareness. Awareness forced study. Study revealed possibility. Possibility required courage. Courage demanded risk. Risk produced result. Each step was necessary. Remove any one step and the modification never happens. Remove the limitation and he never notices the problem. Remove the study and he can't solve it. Remove the courage and he never implements. Remove the risk acceptance and someone else decides he shouldn't try. The complete sequence was necessary, and that sequence only happens when someone is simultaneously constrained enough to see the problem and capable enough to solve it. Most people who are constrained enough don't have the capability. Most people who are capable aren't constrained enough to notice. McLaughlin was both. One-armed and brilliant, limited and resourceful, constrained and creative. That intersection is where this story lives. And that intersection reveals something uncomfortable about progress. Often it takes someone who can't do things the normal way to discover that the normal way isn't optimal. The able-bodied pilots flew Spitfires with heavy controls and adapted. They built muscle. They learned techniques. They made it work. McLaughlin couldn't adapt that way, so he adapted the aircraft instead, and in doing so, he discovered that what everyone had been adapting to was itself adaptable. The system wasn't fixed. It was just accepted. Acceptance is comfortable. Modification is risky. Most of the time, acceptance is wise. Systems usually are the way they are for reasons, but sometimes, rarely, in specific contexts under specific constraints, acceptance is fatal and modification is survival. McLaughlin found himself in that rare situation, and he had the combination of desperation, intelligence, and courage to act on it. On a grey morning over the English Channel, 3 Messerschmitt pilots discovered that one of their assumptions was wrong. The Spitfire they attacked rolled faster than any Spitfire should roll. That incorrect assumption cost 2 of them their aircraft and possibly their lives. The third escaped with knowledge, but without victory. They weren't defeated by superior numbers or better tactics or greater courage. They were defeated by information asymmetry, by facing an opponent whose capabilities they didn't understand, Because those capabilities shouldn't have existed. McLaughlin knew something they didn't. His aircraft was different. That difference was measured in fractions of a second, in degrees of aileron deflection. In the distance, the control stick moved for a given roll rate. Tiny differences, decisive differences. The kind of differences that separate survivors from casualties. When McLaughlin landed after that engagement, his logbook recorded it simply: convoy patrol, 3 EA engaged, 2 damaged. The notation doesn't capture the tactical situation, the modification, the reversal of expected outcome. It's just data. But behind that data is a story about what happens when someone refuses to accept that limitations are permanent, when desperation meets insight, when individual innovation challenges institutional design. Behind those 18 words in a logbook is the answer to a question that every expert must eventually confront. What if the people using your system understand something about it that you don't?